Hi guys, this is Samin. I'll be walking through discussion 5. And so let's get started with the first problem. So the purpose of the first problem essentially is to give you guys some practice applying the equations for approximate Q learning, and then also to understand the update rule and gain some intuition. So in the first two parts, A and B, will just be applying the definition of the Q value and computing some Q values given some defined features. Okay, so if you recall, in approximate Q learning, the Q value is defined as just the weighted sum of features. All features calculated for that state action tuple. And so in vector notation, we can write this as the dot product of the weight vector and that feature vector corresponding to that state action tuple. Okay, so this will give us enough to solve part A and B. So for A, they just want us to calculate the values of these two features they've defined. So feature G has to do with counting the numbers of ghosts, and then feature P has to do with the number of food pellets. Okay, so let's start with feature G. So the state action tuple is the current state and the left action. So at the current state, the value of A is the number of ghosts within one step of state S, so that's just going to be 2, plus B, the number of ghosts Pac-Man touches after taking the action left, so that's going to be 1, plus the number of ghosts within one step of the state that Pac-Man ends up in here. So we're going to count the red ghosts, which is going to be on top of Pac-Man, so ultimately we have 4. And then for state right, we have 2 again for the number of adjacent ghosts, and then 1 for the number of ghosts we encounter, and then 1 for the number of ghosts that are adjacent to us in the state that we end up in, which is here. So that's 4 again. And then for doing up from the state, we currently have 2 ghosts adjacent to us. We're going to encounter no ghosts after going up, and then after we go up, there will be no ghosts adjacent to us. So that's just going to be equal to 2. And then what happens when we do the action stay? So there's 2 ghosts adjacent to us, 0 that we encounter, and then 2 ghosts when 2 ghosts at the state that we end up in, which is just this current state. So that's 4 again. Okay, next for FP. So let's consider state and left again. So the number of food pellets within one step of us currently is 1, and then plus 2 times E, which is the number of food pellets eaten after taking this action, which is going to be 0 for moving left, and this is just 1. And then likewise for going right, we have 1 adjacent and then 0 consumed, and for up, we have 1 adjacent plus 1 consumed, and then for stay, we have 1 adjacent and 0 consumed. Okay, so pretty straightforward. We're going to go to part B now. So essentially, given these features, we want to calculate the Q values for each of these 4 tuples here. So let's just extend this table. Okay, so they're telling us that the weights are -10 and 100, so we calculate this Q value for state left by weighting each of these feature values by their corresponding weights. So we're going to get 4 times -10 plus 1 times 100. So that's going to give us 60. And then we're going to have the same thing for state right. So we're just going to have 60. And then we're going to have 2 times -10 plus 3 times 100, which is going to be equal to 280. And then likewise 60 again. Okay. So likewise, straightforward, just an application of this equation over here. Okay. So in the next two parts, C and D, we're going to be considering the update equation in approximate Q-learning. So recall that in approximate Q-learning, the algorithm works like this. So essentially, we're going to take a step in the environment, and we're going to receive some data. We're going to receive the state that we started in, the action we took, the state that we ended in, and then the corresponding reward. And then using that, we're going to compute a quantity called the difference. Which is defined as the reward plus the discounted version of the V value at state S prime, which can otherwise be written as a max over Q values, like so, minus Q SA. And essentially you can understand this equation as the updated Q value for SA after we've received this data here, and then this is the old value, the old Q value for SA before we receive this data. And the weight update for each weight I is just going to be the old value of the weight plus alpha, some learning rate, times this difference, times the value of the ith feature corresponding to that weight. Okay, so we're going to apply this to, and by the way, you're going to basically just repeat this process. Okay, so for part C, they're telling us that we're taking up from state S and then traveling to S prime, which is just the spot above, and then receiving a reward of 250. So this is our data point that we have to work with, so basically this over here. And then they want us to calculate the new estimate of the Q value for S based on this episode. So like I said, this portion is defined as the new estimate for the Q value based on this data point that you just received. So that is, let's calculate Q new SA. So that's just equal to the reward, 250, plus the discount of 0.5 times the max over Q S prime. So when you're in S prime, the available actions we're told are down and stay. So let's calculate each of these. So we're going to be using the same formula that we used in part A and B. And so using these weights from part B. So the Q value for S prime down is going to be equal to -10 times the value for feature G, which is the number of ghosts within one step, which is 0, plus the number of ghosts Pac-Man touches after taking the action down from S prime. So after we take this action down, we're going to end up back here, and we're going to be touching no ghosts. And then the number of ghosts adjacent to us in our final state here, which is 2. Okay, plus 100 times the value for feature P, which is the number of food pellets within one step of the state S prime. So when we transition from S to S prime, we're going to have already consumed the food pellet. So when we're here, there's going to be 0 food pellets. So that's 0. And then the number of food pellets eaten after taking the action, there's no food pellets on the board anymore. So that's 0. And so that's going to be -20. And then we're going to do the same exact thing for Q stay. So it's -10 times the number of ghosts currently next to us in S prime, which is 0, plus the number of ghosts we'll encounter by staying, which is 0, plus the number of ghosts in where we end up after staying, which is still S prime, so 0, plus 100 times the number of pellets within one step of us, which is 0, and then the number of pellets we consume by staying, which is 0. So again, this is 0. And obviously the max of -20 and 0 is going to be 0. So this gives us that our new estimate for the Q value of state and action is going to be 250. Oh, and by the way, this action is up. Okay, great. Okay, so on to part D. So with this new estimate for the Q value and a learning rate of alpha equals 0.5, we want to update the weights for each feature. So I'm just going to do this in vector notation. So the vector version of this is simply just this update. So let's just perform the weight update. So it's going to be equal to the old version of the weights. So let's put old weight G in the first slot, and then old weight P in the second slot, plus the learning rate times the difference. So we have already calculated part of the difference, right? We've already calculated this part here in the previous part of the question. So it's going to be 250 minus the Q value of state up. And we've already calculated this too, so it's just going to be 280. So that's the difference times the feature vector. So these are each of the features for state up. So feature G for state up is 2, and then feature P for state up is 3. And so ultimately, that's going to give us, and this is 30, -40, and 55. Okay guys, so we'll be doing problem 2 now. So the goal of this problem is essentially to derive the update equation for approximate Q learning. I think it's very important to first read the prompt and then understand it fully before moving on to the problem itself. So we'll be doing that for some context first. Okay, so let's talk about deriving this update equation as we know it. So this update equation here. So in approximate Q learning, you have weights, which you are updating. And if you're going to update something, you have to update it with a goal in mind. So we're going to be updating all the W values in order to minimize some loss function that we define. And this loss function will be a function of each of these weights. And when you have a loss function defined, then the update for each of the weights becomes straightforward. So the update becomes the old value minus alpha, some constant learning rate, times the gradient of the loss function with respect to the weight. So we can try to make sense of this equation. Essentially, the gradient here tells us how to change the weight Wm in order to increase L maximally. But what we want to be doing is actually the opposite of that. We want to change Wm such that we decrease L as most we can. So that's why we're going to be subtracting some weighted version of the gradient here. So that is, in high-level terms, how you do the weight update. So in approximate Q-learning, we've defined this loss function, this L2 loss function, which is defined as this, as seen in the problem statement over here. And if you plug in what they defined for y, then you get this. And then let's try to make sense of this loss function that they've described. So this loss function is essentially encouraging these two values to be close to each other, right? Because we always want to minimize loss, so we're going to try to minimize the difference between these two values. And that actually makes a lot of sense, because if you think back to the Bellman equation, our goal in all of RL has been to try to get the Bellman equation to hold with equality. So you know you found the optimal Q values when this equation holds with equality here. And so essentially here we're trying to change the weights in order to encourage Q to be closer to this value here. So in other words, we're implicitly here trying to encourage the Bellman equation to hold with equality. And of course, as you see, this portion is not precisely equal to the right-hand side of this equation, but that's because this is essentially a sampled version of this expected value. So it's basically a sample drawn from the distribution that the expected value is taken over. Okay, so that's the L2 loss that has been defined for approximate Q-learning. And then, of course, to write out this entire weight update explicitly, we want to actually find the gradient of this L2 loss with respect to each of the scalar weights, the Wi's. So let's compute this. So it would be best. So let's look at this version of the equation and then compute the gradient. So this requires the chain rule. And if you recall, the chain rule just says this. If you want to take the derivative of f of g of x with respect to x, then that's just the same as taking the derivative of f with respect to g times the derivative of g with respect to x. And so in this scenario here, our x is the Wm, the f function, let's say the variable is z, is just 1/2 z squared, where this portion is a z, and then g is just going to be this portion, y minus x. So that makes things much clearer. So what we need to do to find this is to take the derivative of f with respect to its variable, and that's just going to be, bring down the 2, just going to be z, times the derivative of g with respect to its variable, which is going to be minus f of m of x, but technically the state action tuple. Okay, so how did I get this minus f of m here? Well, this equation just consists of all constants except for one single term that is a function of Wm, and that single term is minus Wm Fm. Everything else is just a constant when we're taking the derivative with respect to Wm. And so obviously the derivative of this with respect to Wm gets you negative Fm. So putting this together, we have that this is equal to the definition of z, which is this entire portion inside, y minus wk, fkx times negative fm sa. Actually, we can just write sa here instead of x to be consistent with this. All right, so now we've computed the gradient, and we can just smush it back into this equation here, and after we've done that, we should see that this equation matches with this equation here. So Wm is equal to Wm, minus alpha, but it's actually plus, because let's just bring the negative out here, times, this is essentially, if you inspect it for a bit, this is actually just equal to difference, as we've defined it here, times f of m sa. And so we've derived exactly the update equation for approximate Q-learning, as we see here. Okay, so the premise of the problem now is essentially that they've defined another alternative loss function. This is the L1 loss, which is very similar, except it doesn't have the 1/2 term, and then instead of using the square, it's using an absolute value, which has a similar effect. So now, using this loss function, they want us to redo all of these steps that we've just done here, and then compute the update rule for Wm. So the first part of this is finding the gradient of the L1 loss with respect to Wm. So what's pesky about this is that we have absolute values right here. So we can just break this up into two cases. One case where the value is positive, and one case where the value is negative. So we have two cases. So when L1 is positive, then L1 is just equal to, you can just remove the absolute value bars, and then you get and then the derivative of this expression with respect to the mth weight is just going to be negative f of m x. By the same reasoning as we talked about earlier here. Okay, so second case is when this is negative, and then L1 in that case can just be written as the negation of what's inside. So it's just going to be negative y plus the sum over k of the weights and the features. And then in that case, the gradient is just equal to fm of x. Okay. So now we've shown our work, and we have a chance of receiving partial credit. So in part B, we want to write the gradient descent update rule for Wm. So recall that this update rule is just this, essentially. So aka the new value of this weight is going to be equal to the old value minus some learning rate, a scalar, times the gradient of our L1 loss function with respect to the mth weight. And then we've already found this value in part A, so we just say that this is equal to Wm plus alpha Fm of x when L1 is greater than 0, and then Wm minus alpha of Fm x when L1 is less than 0. So I suppose we can now compare this update equation using the L1 loss function with the update equation that we have when we use the L2 loss function. And they're really similar. The only difference is that the signs and the inclusion of difference over here. Okay, so we're going to be doing problem 3 now. So we're going to pivot slightly to CSPs, which are pretty much unrelated to RL. And in CSPs, you have variables and then domains of the values that each variable can take on, and then some constraints between these variables. The goal is to find an assignment of values to variables such that all the constraints are satisfied. So they've told you what the variables are and what their domains are here. And then in part A, they just want you to define what the constraints are. So let's start with unary constraints, aka the constraints involving only one variable. Okay, so looking at this, we know that x2 cannot be a pit. Otherwise, it would generate a strong wind at this intersection here. And then likewise, x3 cannot be a pit for the same reasons. There would be s's here. And then x4 cannot be a pit either. So we can write x2 is not equal to pit, x3 is not equal to pit, x4 is not equal to pit. And those are the only unary constraints that we can find. So let's talk about the binary constraints involving two variables. So the first set of binary constraints involve the pairs of variables in adjacent boxes. So essentially, either x1 must be a pit or x2 must be a pit. Otherwise, we would not be able to generate a strong wind at the intersection. So x1 or x2 equals pit. And then likewise, we can do this for every pair of adjacent corridors or boxes here. So x2 or x3, something has to be generating that weak wind, so one of them has to be a exit. And then x3 or x4, one of those has to be an exit as well. And then x4 or x5, one of those has to be a pit. And x5 or x6, one of those has to be a pit. And then for x6 and x1, one of those has to be a pit. Okay, so that's the first set of binary constraints. Second set of binary constraints is what we're told in the problem statement, which is that no two exits can be adjacent to each other. So that just means for all ij, such that xi, xj adjacent, they cannot both be exits. Okay, so that's those are the constraints. All right, so moving on to part B. Essentially, we're going to be assigning E to xi, and we're going to perform for checking after we assign. So we also want to enforce the unary constraints, so let's just do that first because it's easy. So unary constraints are that x2 through 4 cannot be pits. And we're going to do for checking now. So for checking essentially means that when you make a variable assignment, you want to look at all the variables which have constraints with the thing that you just assigned. So that will be x2 and x6 for x1, because those are the corridors next to the first corridor. And for each of those variables, you want to prune the domain of any values which conflict with the value you just assigned. So if we look at x2, x2 cannot be a ghost if x1 is an exit. Otherwise, we wouldn't have a strong wind at the intersection of those two corridors, and it cannot be an exit either. And then if we look at x6, x6 can be a pit, because then we'd be able to generate that strong wind, but it cannot be a ghost or an exit for the same reasons. So just to analyze this, we've now made an assignment which has caused one of the domains of the variables to shrink to 0, which means there's no assignment possible where x1 is equal to e. Okay, so now 3c. So we suppose that forward checking returns this set of assignments, and we want to choose the next variable to try assigning values to using the heuristic called minimum remaining value. So minimum remaining value just says that we should choose the variable which has the smallest remaining domain next in our search. And this is intuitive because the variable with the fewest domain values will probably cause backtracking very early on. So it'll probably cause backtracking in the next couple of steps, and this is preferred because we want to backtrack early on in our search rather than later on, so as to not waste time exploring. So again, we want to choose the variables with the smallest domain, so that's just going to be pretty straightforward, x1 or x5, where the tie breaking is arbitrary. Okay, so part D. Assume that we somehow know that the true value of x6 is g. We should list all the solutions of the CSP. So you can do this by hand executing the search algorithm for CSPs, but it's much easier to just eyeball it. So let's go back here. So we're told that the 6th corridor is equal to g, which means that 1 and 5 both have to be pits. Otherwise, we wouldn't be able to generate these strong breezes here. And for 2, 3, and 4, there's actually a variety of satisfying assignments. So one of them is we could put an exit here. If we had an exit here, we would need to put a ghost here, because according to this, the thing here is either an exit or a ghost, and it cannot be an exit because two exits cannot be adjacent to each other, so it must be a ghost. And then we need a weak breeze here, so that's an exit again. So EGE. Okay, so that's not the only possibility. Another possibility is if you assign this to G, and then you see that this has to be an exit here in order to get that weak wind. And this cannot be an exit because two exits cannot be adjacent to each other, so it cannot be a pit either because then we'd have a strong wind here. So in that case, we would have another ghost. So GEG. And these are the only two possibilities because we considered the only two possibilities for 2, and then the rest of the assignment was induced by that choice. So these are the only two possibilities. So for part D, I will just write it here. The two possible assignments are from x1 to x6, just equal to P, G, E, G, PG, or P, E, G, E, PG. And so that's it.